So this second method for solving is what you're typically going to do if you do not have a B, a little center section. So if you remember in standard form, it looks like this, ax squared plus bx plus c. So if your b is a 0, you're just going to have an x squared and a constant. All right, and so when you have that, it's usually easiest to solve by taking the square root. You don't have to worry about factoring. You can just solve by taking the square root. Now, this is a special case, x squared minus 81. If I were to tell you to factor that, this is a special case, x plus 9, x minus 9. And so if I were to solve this by factoring, I would say, well, this is the special case where I have my conjugates. And you can see that you would get positive 9 and negative 9 as your answers. But when you're solving by taking the square root, what you're really trying to do is you're trying to get this x squared all by itself. And so instead of doing the factoring method, you can actually just get that x squared by itself. You would add your 81 over, and you would have x squared equals 81. When you have something squared, like a variable, equal to a number, you can take the square root of both sides. And so if I take the square root of this side and the square root of this side, the square root of a square is just the variable. So x squared with the square root is just going to be x. When you have a variable involved, we all know that the square root of 81 is 9. But when you have a variable involved, you have to consider the positive and the negative root. And so if I were to do this, I would say, yes, it is 9, but I have to consider the positive and the negative root here. Positive or negative 9 would actually be my answer. And so you can see that when I did the factoring, I got positive and negative 9. But when you have just an x squared, you can just get it by itself and take the square root of both sides. All right, and that's actually the rules. If you look at the bottom of page 201 there, simplifying radicals, the first thing you need to know is, how do I take a square root? It's really simple if I have 81 or 36 or 100 and I'm doing the square root. That's beautiful. I know what the square root is. But if you do not have a perfect root when you're solving by this method, you do need to remember how to simplify those radicals, those roots. And so simplifying radicals is at the bottom of that. Write it as a product of prime factors. So I usually recommend using a factor tree. And so we're going to review using factor trees. Simplify the roots with the perfect powers. Anything that pairs up can come out. If it does not pair up, it stays in. If you take multiple things out, you multiply them. If you leave multiple things in, you multiply those as well. If you have a radical in your denominator, it is not standard form to leave a radical in the denominator, so you do have to multiply the top and bottom by that radical. And so we're going to do a couple of those. Simplify. All right, so let's look at this first one. If I have something big like this, I'm going to recommend using a factor tree. So if you don't remember factor trees, this is all the way back from, we did them probably in Algebra 1, and you would have done them in middle school as well. All right, you either used a factor tree or a factor ladder. I don't know how you did it, but same concept. I typically always do the smallest prime on the left, smallest or at least the easiest prime. So when I look at 450, I think, well, 5 is going to go into that because 5 goes in anything that ends in a 0 or a 5. All right, so I put 5 there, and I'm basically just dividing. 450 divided by 5, well, 45 divided by 5 is how many times? Right, 9, yes. And then I can put a 0 there because it's 90. And then 5 is going to go into that again. 5 goes into 9 one time, and then into 48 times. All right. And then I'm going to look, well, 5 doesn't go into this, but what does go into 18? I can say, well, a 2 goes into 18. And then I have a 9. 2 and 9 make 18. And then 3 and 3. When you get to all primes, you're done with your factor tree. All right, you're done with your factor tree. Now, here's where it is. If it pairs up, it goes out. If it is single, it stays in. All right, so if it pairs up, it can come out of the root. If it's single, it's going to stay in the root. And so I am going to say, well, the 5s pair up. I have 2 of them. So a 5 can come out of my root. The 3s pair up. That can also come out of my root. You will notice that the 2 does not have another 2. So the 2 is going to stay inside of the root. All right. It doesn't matter if they're side by side. It doesn't matter where they are in the factor tree. If there is another one of them, they can come out, okay? Pairs come out. If more than one thing comes out, you're going to multiply it. So I have 3 and 5 that came out. So I have a 15 on the outside. If I had had multiple things on the inside, I would have multiplied those as well. All right. And then I am done with that particular radical. All right. Let's look at the fraction. Fractions are actually handled the same way. You just do them individually. And so you can think of this fraction as the square root of 50 over the square root of 3. All right. And so I'm going to take them individually. I'm going to take that 50 and I'm going to do exactly what I did on the left-hand side there. I'm going to split it up. You can see that I have a pair here. So the 5 can come out. The 2 will stay in. All right. And then I have the square root of 3 on the bottom. Now 3 is already prime. I cannot split that up anymore. So that is as factors as I'm going to get it. But standard form for radicals is that I do not have a radical in the denominator. All right. And so the way to get rid of a square root is to multiply it. So if I were to multiply this by the square root of 3, if you'll remember, square root of 3 times the square root of 3 is just square root of 9. And what is the square root of 9? 3. So when you multiply a radical by itself, a square root by itself, you get rid of the root. All right. That's how you get rid of a root. Now with fractions, if I multiply the bottom by the square root of 3, I also have to multiply the top by the square root of 3. All right. Because I'll change the fraction if I don't do that. So on the top here, I have a 5 on the outside, and then I have a 2 times a 3 on the inside. So I have square root of 6 here. All right. On the bottom, I have square root of 3 times the square root of 3. All that does is get rid of the root. So on the bottom, I just have a 3. Now I want to tell you this because this is one of the most common mistakes. You can only reduce outside to outside or inside to inside. All right. So what I mean by that is I can reduce the 3 and the 5 if that was reducible. Let's say that was in a 6 out here. Or I could reduce inside to inside. All right. I cannot reduce 3, which is outside of a radical, with the 6, which is inside of a radical. All right. I cannot reduce outside and inside. So this one is done. 5 square root of 6 over 3 is as simple as you can get this. You cannot reduce this anymore. Okay. If I had something reducible with the 3 over here, I could reduce it. Or if I had a radical down here that was reducible with the 6, I could. But at this point, I'm done. All right. All right, so when you're solving, you have to know how to simplify those radicals, and you have to know the process to actually solving. You are going to want to get that variable squared completely by itself, all right, including the coefficient. And so the first thing I'm going to do is I'm going to move this 100 over. So I'm going to add the 100 to both sides. I'll get 3x squared equals 100. And then I am going to divide by that 3. And now I have the x squared completely by itself. And I can take the square root. So if I take the square root of both sides, I get the x by itself. And I get, don't forget, the positive or negative root of the square root of 100 over the square root of 3. Square root of 100 is one that hopefully you know. Plus or minus 10 over the square root of 3. And just like we saw when we were simplifying, we need to get rid of the radical that is in the denominator. So we're going to multiply the top and bottom by the square root of 3. So my final answer for this particular one is going to be x equals the positive or negative 10 square root of 3 over 3. And you can put it just like that with that positive and negative in front. But don't forget the positive and negative, because that represents two answers. That represents positive 10 square root of 3 over 3 and negative 10 square root of 3 over 3. It's actually two numbers there. This is just a shortcut way of writing those two numbers. There are going to be times when you move something over and you have a negative number and then you're taking the square root. And so in the real number world, if you have the square root of a negative number, your answer is going to be no solution, because in the real number world, the square root of negative 1 does not exist. However, we have assigned a constant. It's actually a constant. We've assigned the letter I to represent the square root of negative 1 so that you can move forward with certain problems when you get a negative in the root. So it doesn't stop you from being able to go on with the problem. All right, and so this is called the imaginary unit I. And we're going to do a lot more in the next section, in the next few minutes with this. But there are going to be times when you try to solve these and you have a negative in your root. Anytime you have a negative in the root, your answer is going to contain an I, because the way you get the negative out of the root is to multiply by negative 1 inside the root, which takes it out with an I. So I represents the square root of negative 1. All right, and so if I were to look at different problems, I can say, well, if I have a negative in my root, I can pull it out of the root with the letter I, which represents that imaginary unit. They do point out, which we're going to get to a little bit in the next section, I squared then would equal negative 1, because if I take this and square both sides, I just get rid of my root. All right, and so this is what's going to happen with this problem. When we go to solve it, our rule is to get that z squared by itself. And to get the z squared by itself, I have to subtract 45 from both sides. So I get z squared equals negative 45. Well, you can see that if I take the square root of both sides, I have a negative here in my root. And what this rule allows us to do is to say, well, this is going to equal I, and we still need the plus or minus, square root of 45. I can pull that negative out of the root with that unit I because it represents that negative 1 inside the root. And then I'm going to treat this exactly like I would any other root. I am going to do my factor tree. I'm going to say, well, the 3's pair up, the 5 does not. And so z is going to equal positive or negative 3i. I still have the I there. Inside my root, I have a 5. All right, so if you end up with a negative in the root, then you can pull it out with an I. All right. Property. If x squared equals k, and then there's some scenarios, k is larger than 0, you're going to have two real solutions. So let's say you have 16, that's bigger than 0. Well, if k squared equals 16, it's going to equal the positive or negative root of that, positive or negative 4. If it equals 0, you're only going to have one solution because the square root of 0 is just 0. You don't have positive or negative 0. If it is less than 0, you're going to have two what's called complex solutions. Complex is imaginary numbers, which we're about to do, a whole section on complex numbers. And so if it is less than 0, you're going to have complex solutions or imaginary number solutions, all right?